We are back with 2.3. We are building up our way to define the derivative shortly. We've talked about limits, different kinds of limits. We need to progress to this idea called continuity. So continuity is critical for developing calculus and the idea of the infinitesimal and the derivative. So that's what this section is all about. Here's the definition of continuity right there. We say a function f of x is continuous at x equals a if, and sorry my writing's a bit sloppy there, but that's the limit of f of x as x approaches a if that limit is equal to f of a. So in other words, the limit value is equal to the function value. And if you remember, what is a limit all about? This is the y value that we are approaching as x approaches a. Does not matter what happens when you actually get there. As you approach, as x approaches a, what value does the function approach? Or what value does the y value approach? We're going to say it's continuous if it equals what you would expect, the function value. So continuity is really just getting at when your limit answer really equals what you would kind of hope and expect. But okay, we'll see what that means in a graph in a second. Let's go through some examples of what is not continuous, and then we'll see what is continuous. I think it's explained best that way. Okay. So I've got this other piece of paper here to block what's happening on the right side of the screen. I'm just going to kind of pull this down a little bit. So I've got a picture here of an example. So let's say that's a function f of x. Okay. And where the point in question is right here. So we're going to call that a. And we're going to say, hey, for this graph with that a, is the function continuous at a? And instinctively, usually when I pose this question to a classroom, everybody says no, that's not continuous, because that violates our natural understanding probably of the word continuous, and that would be absolutely right here. This is not continuous at a. Let's think of it a little bit deeper, maybe in terms of how we're defining continuous with the limit equaling the function value. What's going on with the limit there at a? You might say, well, on the left, it's going here, but on the right, it's going here. Well, if the left and the right are not going to the same place, then the limit does not exist. The limit of f of x as x approaches a is d and e, because the left side and the right side are not equal. Well, if the limit doesn't exist, certainly it can't equal anything, and so this is not going to hold, clearly. Now we're going to give a particular type of name to different discontinuities. This one is called a jump, and maybe for obvious reasons, the function, this is kind of a piecewise function, right? And it has this jump, and we even used that word before when we were talking about limits, and limits being d and e. Okay, so I got another one coming up right down here. How about this picture? So there's our function. And now what's happening at a? Well, I don't think my line is quite where it should be, but okay, you get the idea. What's happening at a? Now there's a hole. So we had a jump a moment ago. Now we've got a hole. Well, if I was in the classroom, I'd say, what do you guys think? Is that function continuous at a? And again, most people would say, no, that doesn't fit my understanding of what continuous is. At least that's been my experience in teaching this, and that would be right. This is not continuous either. Now let's look a little bit deeper. The definition says the limit of f of x as x approaches a is supposed to equal f of a. Well, now this time the limit does exist, right? Let me pull this up a little bit. that limit does exist because the left side and the right side are going to the same location. So wherever that y value is, which isn't labeled, but that's okay, the limit does exist. However, in this drawing, the function value is what's D and E here, right? I don't see any point there at A, and it's not there, but it's nowhere else either. Well, so if the function value doesn't exist, certainly they cannot equal each other. Okay, so it's not continuous. We're going to call this one a removable discontinuity, and I kind of like that name because it's as if somebody reached down and just like plucked that point out and took it and threw it away. So that one point at A has been removed. Now that said, we're talking about it being continuous at A. It is continuous at other points, just not at A. Okay, so we'll talk about what continuity looks like in a little bit. But here, not continuous at that one point A. All right, now we're going to go to the other side of my paper here. I'll just show you this part. Okay, so there's the next drawing. Oh, I'm showing you too much. Pretend you didn't see that. Let's do a similar drawing to the last one, except now we're going to put a point there just above that hole, let's say. It could be above, it could be below. Doesn't matter. Is this continuous? And my experience in teaching this, when I say that to a classroom, is everyone says, no, that's not continuous either. I'd say, okay, yeah, you're right. Why not? Now this time the limit exists, right? Left side, right side, going to the same spot. Now the function value exists. It's up here, but the two do not equal each other. So we would get a value for the limit. We would get a value for the function at A, but they're not the same y value. So they both exist. They just don't equal each other. So you can't be continuous. You have to be equal to each other to be continuous. Okay. We are going to label this one a removable discontinuity as well. Kind of for the same reasons. It's like somebody reached down, plucked that one up, and they removed it, but then they set it back down somewhere else. Okay. Let's move on. I got one more drawing here of something that is not continuous. Let me go ahead and show you this. Okay. So you've got this drawing, and now we're putting a vertical asymptote there at A. And so we see the graph and kind of typical behavior around a vertical asymptote. We've got this sort of thing, but right there's the asymptote. Well, would this function be continuous at A? And well, no, okay, definitely not. Right, there's a vertical asymptote there. And we almost think of it as like this huge jump, right, between this is going up and this is going down. Is this a jump discontinuity? No. And let's kind of get into the details. So you see the name there. In this case, the limit does not exist. The limit of f of x as x approaches A, right, because the left side and the right side are going to different places. And the function value doesn't even exist. Nothing exists. Oh, well, okay. Then we can't say they're equal if neither one of them are there. We call this an infinite discontinuity because they're infinitely far apart. So it's almost like an infinite jump, but we don't call it a jump. We just call it an infinite discontinuity. All right. So those are the three types of discontinuities: jump, removable, and infinite. And now finally, let's see a drawing of something that is continuous. Here you go. When nothing unusual happens, you might say, there's no jumps or holes or vertical asymptotes. In this drawing, right, there's f of x, there's A, and the point is just right there on the curve where you would expect it to be. So the limit of f of x as x approaches A, well, it exists because the left side's going to the right side, right? And whatever that value of that limit is, that's where the function value is as well, so it all matches up. And so here, this is continuous, let's be really clear, at A. In fact, this drawing would be continuous at all of these other points as well. And some of those other drawings that we had certainly would have points where it's continuous as well, just not at the point where not at the point that we're highlighting. Okay. So kind of at the end of the day, if nothing unusual happens, then it's going to be continuous. No jump, no hole, no vertical asymptote. It's right where the point is, right where you would expect it to be. Okay. So where to go from here? Let's take a look at this question. So we're going to be given a drawing. You might remember this drawing from the beginning of 2.1 when we first introduced limits. Let's take a look at it again. State all x values where f of x is discontinuous. Okay, it's actually more interesting to point out the locations where something's discontinuous usually. But once we have those, then we're going to state intervals where f of x is continuous. So we'll use interval notation to name all of the points that it's good where it is continuous. Okay. Well, let's think. This is a closed dot, by the way. Close, closed, open, closed, open. All right. All of the x values where f of x is discontinuous. So if we start over here, we say, no, everything looks fine. There's no jumps, no holes. No jumps, no holes. Okay, right there, there's a jump. So it's going to be discontinuous at 1. And then we keep going. Okay, well, there's a hole. So it's going to be discontinuous at 4. So it's discontinuous at 1 and at 4. And I'll just show you everything here. Now, this question, so there's our answers. X equals 1, x equals 4. Now, if we wanted to go a step further and be prepared for this, I forget what the homework does, but definitely be prepared for it on a quiz or a test. Be prepared to name which type of discontinuity is occurring at which x value. Okay. So we kind of did it as we were reading them, right? That's a jump, and so it's a jump discontinuity. That's the type. And then this one at the hole, well, we don't call it a hole discontinuity, we call it a removable discontinuity. But hopefully that's not too big of a leap. So we can even name the types. Now then, if we wanted to state the intervals where the function is continuous, then we'll use interval notation, and we'll just be sure to jump over 1 and 4. So we might say negative infinity to 1, union 1 to 4, union 4 to infinity. So we're just skipping over those two moments at 1 and 4. But it is continuous everywhere else. Okay. All right, now it's all fine and well when you're given a graph. But what if you're not given a graph? What if you are given, oh, I think I need my other paper here. What if you're given just the function like so? And same question, we're going to state all x values where f of x is discontinuous, and then we're going to state the intervals where the function is continuous. Okay, so let's begin with the x values where it's discontinuous. That's usually where you have to start, and then from there it's not too bad to get the intervals where it is continuous. Okay, well, where might this be discontinuous? And so you're going to think to yourself, well, I don't know what that graph looks like, but certainly if you were ever to divide by 0, then that'd be a problem. And yep, if you were to divide by 0, one of two things could result. There might be a vertical asymptote there, or there might be a hole. And we've dealt with those sort of things in the review and previous, even in the sections, distinguishing holes versus vertical asymptotes. So both of which come from dividing by 0. Okay, so let's think, how can we find the x values where we divide by 0? And you think, well, let's factor that denominator. Okay, so I'm just going to take that, and this is f of x again. We could probably write that if we wanted. So that's x minus 3 over x minus 3 times x plus 1 when you factor that denominator. Okay. And so we can tell there is a place where there's a hole, and there is a vertical asymptote. The factors that cancel would give you a hole. The one that does not cancel would give an asymptote. So where it would cancel would result in x equals 3. The one that does not, x equals -1. And let's just go ahead and label what's happening. We don't need to see the graph, right? We know that's what's going on there. Okay. And now we're good. We can answer this question. Where is this thing discontinuous? Well, at x equals 3 and x equals -1. And if we wanted to go one step above and even name which types of discontinuities we have, then we can do that. So if there's a hole, well, remember that's removable. Kind of makes sense. The point has been plucked out and thrown away. And if there's a vertical asymptote, we call that an infinite discontinuity, right? Because the two sides are infinitely far apart. Okay. Now, once we know where it's discontinuous, not too hard to state the intervals where it is continuous. We just, give the interval notation with those 2 points removed. And there it is. So again, we've got these two locations, kind of like the last one. -infinity to -1, union, -1 to 3, union 3 to infinity. At every one of those points, it's going to be continuous. It's going to be nothing unusual happening anywhere else, just at 3 and -1. Okay, I think this has been great. We've gotten a long way. Another video coming up next.